In memory system, have seen few basic things, but now there are more details that has to be discussed. Okay, so let me share my whiteboard. Can you see my screen?
Yes, sir.
Okay. So we already know that we have a memory. This memory is organized in form of cells. I think there is a problem. Okay, let me reshare something else. This is not working properly. Okay, so let's do with it. Fine. Just hold on for a minute. Yeah. So we know that there is a memory. Is it audible? It is visible? Is it visible?
Yes, sir.
Okay, and this
Yes,
memory
sir.
is in form of cells. What these cells are, we'll talk about those little later. But generally, we use word addressable. Memory, or it may be byte addressable. Do you remember what is word addressable and what is byte addressable?
Yes, sir. Yes, sir.
So where we are addressing a word and where we are addressing a byte, and if the word size is it is typically same. So it depends on the number of address lines. That what will be the size of memory? What is the possible size of memory? So, for example, if we have a 16 address lines, what may be the size of memory if it is byte addressable? Can somebody tell me?
So could you repeat the question?
So if we have 16 address lines, in system, what will be the possible size of memory that this system can support? And memory is byte addressable, we know. Oh, you guys have completely forgotten.
Sir, 2 to the power 16?
Yes, it is going to be 2 raised to the power 16. Why 2 raised to the power 16? Please tell me, someone. Hmm? Can somebody tell me? Okay, so given the 16 bits,
So, yeah.
yeah,
So given this 16 address and there are 2 raised to 16 Combinations that they could be in.
So you can generate as many as 2 raised to power 16 combinations, and each of these combinations will be treated as one address. So in a way, you can have 2 raised to the power 16 addresses if you have a 16 uh, address line system. So those addresses, if it's a byte addressable thing, it will be 2 raised to the power 16 bytes that can be supported. If it's a word addressable thing, 2 raised to the power 16 words that can be supported. Right? Is it okay? And apart from that, so when there is a memory, so there are 2-3 things that has to be, controlled in this. One, you have to tell that what location you have to access. So that means what will be the address that you are interested in going to. Then another question is whether you are interested in read or write. So you are interested in read or write. That may be another question. And then, of course, final thing is for which everything is being done is data. So while dealing with memory, typically you need these 3 kind of things. One is address that tells you which location you want to access. Second, maybe few control signals. I am just writing most important of those. So whether you want to read at that location or you want to write at that some location. And then if you are reading, the data should come out. So in this way, if you're writing, data should go in this way. So typically these are the 3 things that actually comes into picture when you're dealing with a memory system. Does it make sense? Is it okay?
Yes, sir.
So now let's see a very simplistic block diagram for a memory system and processor. So I'll have a processor, and then I'll have a memory system, and then something will be going for address. So if you remember, can you tell me from where, which register this address will be going to? If you remember a bit, I have discussed that in previous classes. Can you tell me from where, which register this address is going to?
Program counter,
No, not program counter.
address register,
Yeah, so you call it MAR. MAR stands for
Memory address register.
memory address register. Exactly. So it will be a k-bit line. The example we gave for that, it will be a 16-bit line, but otherwise, in general, it will be a k-bit line. Then there will be data flowing through. Here we will have another register. What will be the name of that register?
MDR.
MDR, precisely, yes. So that is memory data register. And then there will be few control lines. So those control lines will be like read and write. Generally goes on the same line, same line. That's why we write it like this. And then MFC, etc. depending on the capabilities. Here we'll be having up to 2 raised to the power k addressable locations. if this is n bit, so our word length will be n. In fact, other way around it is the right. If the word length is n, this has to be n bits. Right? Is it okay? So processor reads data from memory by loading the address of the required memory location from MAR, and then set this read write thing. So, I mean, depending on what you are doing, whether reading or writing. So it will be, if read operation, you will be setting it to 1. If it's a write operation, you will be setting it to 0. And then as a result of this process, memory will be putting data here or will be taking data from here. So if it is 1, if r is equal to 1, or in fact, yeah, I should not say r, I should say r w bar is 1. The data will be placed here, and after placing the data, this MFC signal will be sent. So this MFC signal will tell the processor that memory function is MFC stands for memory function complete. So after asserting this MFC signal, processor understands that memory has done its work. So now there is data available over over data lines. So that I should copy to memory data register. Make sense? Is it okay?
Could you repeat the MFC part again?
MFC stands for memory function complete. So if I am talking about a read operation, so what will be the memory function in this? Memory function in this will be that when you receive the address location by which you have identified, suppose this is the location that has been identified, and you got the idea that this content of this location has to be read. So the memory function is to put in this data on the bus. So as soon as this will be put in on the bus, MFC signal will be asserted by the memory, and as a consequence, the processor will understand that now the data is available over the bus, and it will take this data from the bus. If it is a write operation, that means it is 0. Memory data register will put some data here. As soon as this memory guy will read this data, MFC signal will be asserted here, and processor will remove this from the bus. Make sense?
Yeah.
Is it okay? There are two kinds of data transfers that are possible. You already know. One is block transfer, and another is the one-by-one transfer. So if there are consecutive address locations involved, we call it block transfer. You already know that. I'm just reminding you this, right? And all this process, as previously, is synchronized by clock. So now there is something important that has to be understood. So there is something called memory access time. somebody tell me what is memory access time? Hmm? Can somebody tell me what may be memory access time?
The time it takes to identify the address.
No. So the time from read signal, if it's a read operation, signal to MFC. This time is considered as memory access time, right? And then there is another quantity that is termed as memory cycle time. So if there are more than one memory operations happening, so the time between two successive memory operation. Does it make sense? Hmm?
Yes, sir.
Does this make sense? Now this is the right time to ask the question, what do you mean by RAM? You are using RAM, I think, at least from 10th. You are using this word since 10th, or I think even earlier. I don't know. I mean, for our time it was different, but now even you are reading it, even before that. So what does a RAM means?
In the memory, we can randomly access any address.
What does it mean?
Uh, it means suppose we have a block where there is a continuous array of addresses, right? So we need not go through them sequentially to reach an address which is in the middle. We can randomly access that.
You can do in all kind of memories. Why this memory is only random access? So it is related with memory access time actually. So the idea is memory unit is called random access if any location can be accessed in fixed amount of time. Doesn't matter where this location is. And this makes it different from your secondary memory where there are tapes involved, there are sectors and all that. Right? So, I mean, of course, you can say that all semiconductor memories are of random access type. Yeah, that's right in a way. But these tape memories and all are actually not random access. Now, there is another important thing. So there is a processor and then there is a memory. What processor is doing? So processor is, I mean, going to memory, reading some program. Program is being transferred. Program is the line of program actually is transferred to MDR, and now this MDR is getting to your I mean ALU and CU. Sorry. So this is going to ALU and CU, and this is being executed. And of course there will be registers that will be the part of this.
So are you there?
उनका इंटरनेट कनेक्शन इशू होगा शायद.
Hello, hello.
Yes, sir,
Yes,
you're
sir.
audible.
Yeah. So till what point I was there in the class? Can you tell me?
So you were going on after explaining RAM.
Oh, so I could not discuss anything about cache. Did
No,
you any?
sir.
No, sir.
Did you hear anything about cache? No.
No.
Fine. Okay. So let's restart this. So yeah. So let me do it again. So there is a processor that has got its ALU and CU, and then there is a MGR.
So have you
Sir, you're
shared
not
your
sharing
screen?
your screen.
Oh, my screen is not shared. Sorry, I forgot. My screen is visible
Yes, sir.
now.
Yeah.
Can you see my screen? So I've written MDR, ALU, and CU. You can see that, right? And then there is a memory, MDR, or you can say IR. So there is, I mean, MDR and then IR and then ALU and CU, right? So, and there is a memory. So what happens? Processor goes here, fetches instruction from memory. Instruction comes to MDR, then it goes to IR, and then ALU and CU performs the required operation, right? In this process, there are two things. One is processor execution time, and another is memory access time. So, if these times are on the same level, this is not a problem. But what is happening, because memory access time is high and processor execution time is low, this memory access time actually acts like a bottleneck for whole of the system. So even if you can run faster, you cannot run because you are not able to get memory faster. You're getting my point?
Yes, sir.
So then the solution that is proposed is, and you are aware of that solution actually. So this is my processor and this is my memory. And I have drawn one other box connected with it. Can somebody tell me what this box is? Hmm?
So primary memory.
So I have already drawn memory here, right? This box I am talking about. So can you tell me what this
Cache.
box is? Cache, actually. So this cache is something that is acting the first source for the processor to fulfill its requirements, and eventually this is taking data from memory and providing processor. Many times processor direct go to memory as well. We'll discuss all that. But this small, and this is actually very small. This small part makes things quite fast. So this is cache memory, and generally it is pretty small in size. And why it is pretty small? Because it is really expensive to have this kind of memory. Many times, rather generally, it is sharing the same chip as processor. So I mean, you cannot afford to have a larger cache, but even smaller cache works in a pretty decent manner. There is another idea that is called as virtual memory. Can somebody tell me what is virtual memory? Hmm? Any idea from anybody? So, if you have, let's say, k addressing capability, and you have memory of, let's say, m size, where k is greater than m, and when I am saying memory, then I mean primary memory. So if you have less primary memory than a processor can actually address, then what you do, you use secondary memory, a part of secondary memory actually, as primary memory. So this particular secondary memory that is actually secondary but used as primary, this particular portion of memory is called as virtual memory. How we do that, that is pretty much same as cache, but this is actually increasing the uh, effective size of primary memory. Make sense? We'll discuss about these two things in detail later in the class, but for now, is it okay? Hmm?
Yeah, sir.
Now, we'll see about the memory organization a bit, and then we'll move on to the cache and virtual memory later. So, I am just drawing a figure. This is an example of small memory unit. This is my address decoder. And then there are memory cells all over. So these are my memory cells. So these all are data input output lines. These B1, V7, B1 and B0. I don't know if you can read this B0 or not. Data input and output lines. So basically these are data lines. Data input output. These are address lines. So I'm talking about a system that is actually having. So this may be W15. So how many lines will be here? Can somebody tell me? Huh? It's a, I mean, 16 byte memory.
4.
So there will be 4 lines. Of course, A3, A2, A1, and A0. So this is a very small organization of a memory chip. These boxes where nothing is written, you can take them as memory cells, mostly flip-flops. Then you can see that there is a horizontal line connecting to all of them. That is address decoder's line. So these 4 inputs will generate one of the line high. Decoder will make one of these W1, W0 to W15 high. So that line will be selected. And then there are 8, I mean, you can say cells in one row. So those 8 cells will be selected, and then you can see that there is a they all are connected to a below data input output line where read and write operations are possible. So does it make sense to you? So all that will happen is this A0, A1, A2, A3 will select one of the rows, and from that either some data will be written into that by this data input output line, or some data will be read through it by these input output lines, data input output lines. Does this make sense? So it's a very small circuit. Does this make sense to you?
Yes.
Is it clear to everybody? Okay, so now let's see a slightly different example that will be little bigger in size actually. So now what we are talking about is a 32 cross 32 memory cell array. So in this, if you'll see that this is 1 unit, this is 1 unit, this is 1 unit, and likewise. So in a way, all the memory units are written, I mean, put in separately. If you consider this one as 1 unit, so in actually what you are doing, you are putting this at like this, up to this 16. So this is your cell 1, this is your, or you can say cell 0, this is called cell 1, cell 2, and cell 15. These all are put in one line. Now what we are doing is in the next part of this thing, now we are actually putting them in form of a rectangle rather than in form of a line. So maybe, I mean, you can have a memory organization like this, where you can have 32 by 32. Okay, so this is small, so you can say that it is 5 by 6. Similar way, it can be 32 by 32 as well. So how to, handle that? Just let's see. So when I am saying a 32 cross 32 memory cell array, for example, this is 5 cross 6 memory cell array. I'm there in the class, or I just left out? Hello? Hello?
Yeah, so you're there.
Fine. So this is, for example, a 5 cross 6 memory array. And all of these actually have a complete cell like this. So this complete presents, this complete is actually one cell here. So this is here maybe 1, 2, 3, 4, and likewise 7, 8. So such 32 cross 32 memory cell array is there. Because it's 32, so we have to have 32 lines here. So it will start from W0 and it will go till W31. And of course, there will be a memory decoder. So what will be the number of bits that will be coming input to this? Can you tell me?
2.
Huh?
There are W0 to W3, right?
W31.
31. Oh, so then 5.
5. And similarly here, you'll be having a 32 cross 1 output multiplexer. Mux stands for multiplexer and demux. So here, because again it is 32, so you again need 5 lines here. And here you'll be having read and write or sense or write circuitry. Those also will be 30. And of course, here you will be having a command for R, W bar. And there is another thing that is called as chip select, so CS. So chip select will be there. And then of course, there will be a data input output. So this in all will be 10-bit address. So first, let's understand how will it work. Can somebody tell me how will it work? So first of all, these 5 bits will be inputted, and as a consequence, W0 to W31, these will be selecting one of the lines. So suppose this line got selected. Now another 5 bits will actually choose one of the outputs in this, and maybe this output will be chosen. So this way this output will be chosen, and this data input output, depending on whether it is a read signal or a write signal, this will be used to write the data or read the data. Does it make sense? So in a way, in the previous example, you were actually choosing the byte in one go. Now you are choosing in 2 goes. So in first go, you are choosing 5 bits. That means you are choosing rows. and in the second part you are choosing column, and then you are putting data into that. Does it make sense?
Yes, sir.
Now the question is why we are doing this hanky panky thing, because still we are doing with 10 lines. We can directly use 10 lines and do that. Why we are doing this at all? Any ideas to this? Any suggestions to this? So the idea is, you can probably figure out by now that these 5 lines are needed first, and then these 5 lines are needed second. And when this is needed, this is not needed, and when this is needed, this is not needed. Does it make sense? Is it okay? Does it make sense to you guys?
Yes, sir.
So that means that these lines can be sent in a multiplex form on 5 lines only. So what actually we'll be doing this, so these 10 lines, so this line and this line, they will be coming on the same line. This line and this line, they will be coming on the same line. This line and this line, they will be coming on the same line. This line and this line will be coming on the same line, and this line and this line will be coming on the same line. So in a way, uh, when you want to use this portion, this line will go for this line will go for this line will go for this, and likewise. When you are using this portion, this line will go for this line will go for this line will go for this, and likewise. So a simple 1 cross 2 multiplexer and demultiplexer can reduce the line in half just by organizing the memory in rows and columns. Is it okay? Any confusion about it?
No, sir.
Right. So now let's talk about static memory a bit. I'll just discuss static memory and dynamic memory, and details I'll be discussing in the next class. So, do you have any idea? Anybody have any idea about what is a static memory and what is a dynamic memory? I'm just trying the circuit. For electronics people, this circuit is maybe quite familiar. For computer science, it's maybe a little scary, but don't get scared. I'm just trying to show a simple difference, nothing else. Sorry for my poor drawing. these are the CMOS transistors that are actually placed in one cell of uh, static memory. This is my word line, and this is my bit line. So I mean, probably you can understand word lines means one that is actually selecting the row, and bit line that selecting the column. So for a simple static memory, this is the kind of circuit. Static memory is something where you store something and it stays forever. I mean, as long as you are not clearing this, it is going to stay forever. Then there is another kind of memory that you call as dynamic memory. So this is the diagram of dynamic memory. And this is my word line. So the idea that I want to convey is those static memories are simple to handle, and I mean they can have the memory for longer duration. They can contain the data for longer duration. They are quite complex and expensive. Whereas dynamic memory, though the memory content leaks out of that, they are very simple and cheap. But the point is, if the content is leaking, how to handle that? So there are refreshing mechanism by which you can refresh the data and keep it as it is. So how to do that? We'll discuss that in the next class. By now, I want to the only point I want to make is, dynamic memories are the memories those require refresh of their data on periodic intervals, and static memories are the memories that doesn't require that refreshing. Static memories are expensive and complex. Dynamic memories are simple and cheap. And there is, you can see in dynamic memory, there is a capacitor sign. So there is a capacitor in place from which charge leaks, and that's why you lose the data. Does it make sense? So I'm not interested in going for the detail of this complex circuitry, particularly for static memory cell. I just want to convey the difference in complexity and cost. Does it make sense to you? Is it okay?
Yes, sir.
Is it okay? Okay, so we'll stop
Yes,
here
sir.
today, and we'll discuss other things in the next class.
Okay, sir.